Now we'll formally state and we'll also prove the last theorem of section 4.4, the inverse function theorem. It says that if f is continuous on a closed bounded interval ab and differentiable on the open interval ab, and if the derivative of x is never zero from x going from a to b, then f is one-to-one and continuous and differentiable on its image, f of the closed interval a to b. And more specific, the derivative of f inverse prime of f of x is equal to 1 over the derivative of f at x, or the derivative f prime of x. And that's for all x in the interval from a to b. Okay, a lot to show there. Well, first of all, in the proof, since the derivative is never zero on a to b, that means f is one-to-one on that interval. That was from Theorem 4.19. So it's one-to-one, which means it has an inverse. Let f of ab, the image of f, or you could say the image of f under the closed bounded interval ab, let that equal CD. Now, why are we allowed to say that? The continuous image of a compact set is compact. So if you have a continuous function, f of a closed interval always gives you a closed interval. What we'll show first, for starters anyways, is that f inverse, which is the function going the opposite direction from CD into AB, is differentiable. So we'll take an arbitrary point in CD and show that it's differentiable at that point. So y0 comes from the interval CD. Let yn be any sequence in CD that converges to y0, but it can't equal y0. So yn is a sequence in the interval CD minus that point y0. Well, for convenience here, let's let xn be the inverse image of yn for all n greater than or equal to 0. Another way of saying that is yn is equal to f of xn. All right, so I just made a special note here that x0 would be f inverse of y0. Since f is continuous, by Theorem 3.12, f is continuous because the continuous image of a compact set is continuous. I'm sorry, the inverse function f will be continuous if f is continuous on a compact set. Well, let's see what we have here. Because f inverse is continuous, and because yn converges to y0, f inverse of yn will converge to f inverse of y0. But this is just xn. So therefore, xn converges to this, which we'll just call x0, since it is x0. Those two things are equal to each other. All right, next. I'll move to the right. I'll get f prime of x not equal to 0. I'm going to say given. That's part of the hypothesis of the theorem right here. And f one-to-one implies that f of xn minus f of x0 over n over xn minus x0 is never equal to 0. Xn minus x0 is never 0 because the sequence xn was taken from numbers not equal to x0. And it's a one-to-one function, so if these are different, these are different. So it's never going to be equal to 0. Hence, this sequence, f inverse of yn minus f inverse of y naught over yn minus y naught, which is equal to, I'm just going to do a little bit of substitution here. Remember, f inverse of yn is just xn. Xn minus x naught over f of xn minus f of x naught. All that is substitution there. Those two sequences are equal to each other. And what does this look like? This looks like the inverse, the reciprocal of the thing we need to take the limit of in the derivative definition. And that exists. F is a differentiable function. This converges to not f prime of x0, but 1 over f prime of x naught. It looks like one more sentence, I think. Therefore, by Theorem 4.1, f prime is differentiable at y0 and f inverse prime evaluated at y0 is equal to f inverse prime at f of x naught is equal to 1 over f prime of x naught. So, since we showed that f prime is differentiable at y naught, and as I mentioned earlier, y naught was just arbitrarily chosen, that means it's differentiable in the entire, for all y naughts in the interval from c to d. So it is a differentiable function in that interval, and we've proven what we needed to prove.